Or
you move from
after it all would be more interesting. Because then
Right.
there's some
the
context.
space of the text.
Yeah.
The same question can be
I was thinking about doing something which is a bit.
Yeah, I agree, and I feel like I was like that bridge is not there yet.
exactly. And I think it's like very exciting. Like now, like there's a lot of interactions.
Do it before.
One-to-one.
After it's good.
Yeah, in those cases,
And then the other is
in those cases,
Yeah.
What's the problem that we're thinking?
I think it's just
Exactly.
it's not
Many other
surprising how it's
It's like more where I want to go. Because for that you need the resources. It's more easy to stick with theory because you've already been
I wonder like, well, it's hard to say because cooperative game. Do they always go towards Nash equilibrium because they're just trained?
All right, hey everyone. Welcome back after lunch. Hope you got some nice sunshine and some food. So excited to hear today in this afternoon session first from Chenyu Zhang and Naveed Azizan. So Chenyu is a PhD student at MIT. Naveed is an assistant professor in mechanical engineering and also IDSS, so the Institute for Data, Society, and Systems. And today we'll hear more about their work looking at personalized collaborative learning. So very interested to hear about this, the role of personalization in multi-agent learning. So excited to hear more today. Thanks.
Yeah, thank you. So hi everyone, I'm Chenyu. So sorry, Naveed isn't here. I'm gonna present in his stead. So this talk is based on our recent work accepted to iClear this year, I think we think it's a perfect fit for this workshop because it's not only learning from heterogeneous sources, it's also learning for heterogeneous agents. And we asked the same question as in the description of the workshop, is like how can we model the structure of heterogeneity and the similarity affinity among agents. So I'm gonna first spend some time on the setup of this work because it's a little bit different than federated learning. And I think the ultimate goal of this talk is to convey you that this is a reasonable and exciting setup to work on. And then I'm gonna explain the result we have and try to give you some intuitions of the mechanism that achieves such a result. And then I'll conclude with some future directions. So for the setup, let's first consider a toy example. For example, we have different agents and they have different tasks. And the task here is to match a color they like, and they have different colors to match. And additionally, they have different environments. For example, here is that they have different, for example, pigment tubes. So we have both objective heterogeneity and environment heterogeneity. So the question is like, do they want to collaborate? Because intuitively, if agents are very different from each other, they may not want to collaborate if they only care about their own solutions. And if they do want to collaborate, what is the motivation of such a collaboration? And when do they want to collaborate? For example, many work argue that if they want to collaborate when they're like similar to each other. Is that the case here? And if they do want to collaborate, how do they coordinate?
What does that mean to match a color?
It's just like a abstract map in mind. It's not. We have like a more formal definition and a task here, but this is just a general idea of what we are considering here. Yeah, we're not gonna talk about color matching actually. So the formal setup is like this. So we have different sets. We consider general multi-agent linear system. So it's general in a way that it captures a lot of applications, but it's also very stylized because it's linear system. But we have like many different linear systems. So they have different agents have different left-hand side matrices. And right-hand side vectors. And they only care about their own solutions. So in this setup, there's no central agent or like a general, a global model. So every agent is selfish. They want their solution. So this is a personalized setting. And we assume, this setup is like different than federated learning where you aim for a unified solution for all agents. But here we do not aim for a unified solution. But we do assume like a similar collaboration scheme as in federated learning. So we assume there's a central server that can aggregate information from agents. For example, in federated learning, the local information can be the local gradient, and then you aggregate it into the central gradient. But here, we may communicate other information as well. And we consider learning setup is that the agents do not know their system parameters. They only observe a stochastic estimates of these system parameters. And importantly, like the data for each agent is actually coming from different distributions. So this is what we call an environmental heterogeneity. So again, the linear system, they have a system parameters, and agents only observe a stochastic observation of the system parameters. And the data of this, the sample of this data is actually coming from different distributions. So this is the formal setup of this personalized collaborative learning. And to give a concrete example, oh, yeah, I want to mention the sole assumption here is that the matrix should be positive definite. So you will mimic a strong monotonicity of operator iteration or strong convexity in optimization. And we do not have any assumption on like how different are these objective vectors or how different are these environment distributions. Yeah, we call this B objective vector, and we call this mu environment distribution. Yep. And a concrete example here is reinforcement learning. So for example, we have different reinforcement learning agents, and they have different policies. And the goal here is to evaluate the value functions of the policy. So this is a natural heterogeneous objective because they have different policies. And the environments is, for example, they have different transition kernels, and together with their different behavior policies, they will introduce like heterogeneous stationary distributions. And specifically, the A here in reinforcement learning, this is the Bellman operator. So we evaluate the difference between the current state and next state. And the B here is just the reward signal. So we also can call this like a B vector a reward function. And the data here is just state action sequences. So if this setup is a little bit abstract, you can always think of this as a reinforcement learning agent setup. And the question here is that can agents collaborate to learn their personalized value functions with reduced sample complexity? So again, we ask for personalized value functions, and we want to develop some guarantee that is showing there is some collaboration benefits. So that is in terms of sample complexity. Any questions about the setup? Okay. Yep.
You wanna, so what's the cost function again? Is the cost function exactly wanna learn xi star? Is it unique? Is it, are there many xi stars? What's the cost?
So because we consider a positive definite A, so there's only unique solution, and we'll consider mean square error in this case. Yeah, but we can also consider other errors, but I'll talk about that later. Yeah, so this setup comes with some accompanying goals. The first is that we want to find personalized solutions. That's the first promise. The second thing is that we want to assume the agents are selfish, so you want to show that there are some collaboration benefits for them to be incentivized to collaborate. So in terms, yeah, we consider mean square error. So specifically, we want to show that the mean square error with regard to your solution with collaboration is strictly smaller than doing it alone. And the speed up effect is captured by a parameter called delta, and is kept by 1. So basically, you will never be worse than independent learning, but in some cases, you will have some like speed up due to collaboration. We want to show that. And we argue for learning adaptivity. So basically, not only the agents do not know the system parameters, they also do not know how heterogeneous they are. So the algorithm should be adaptive to that heterogeneity. Specifically, if the agents turn out to be very homogeneous, then we want the delta to be converged to 1 over n, which recovers the linear speedup in federated learning, which is optimal. And then if the heterogeneity is unbounded, like there's nothing alike between agents, we want the algorithm to return a delta that is kept by 1. So that will reduce the learning to independent learning, the worst case, which is also we'll show that it's optimal. Yeah, so these are the three goals matching the three key components of the setup. Yep. Okay, so I hope this setup makes sense, and I want to argue that the personalization is pretty important. It's a key focus of this work. So there's some discrepancy between this setup and the federated learning setup. And the result we have, so I want to briefly review some related paradigms. So there have been many works that are targeting personalization. So we have two baselines. I think this is very familiar to all of you. The first one is independent learning. So we use different colors to represent different tasks, and use the height of the column to represent the complexity of that task. So for example, if you do it alone, then you need to spend 4 units of effort. And if you use federated averaging, you only need to spend 1 unit of effort because of the bias variance trade-off. However, the solution you get is a unified solution for all agents, which has a huge bias with regard to your solution. This is not desired if we collaborate with very heterogeneous agents. And there's some effort towards personalization, for example, clustering methods. However, for a clustered method, within the cluster, you still have some heterogeneity if the granularity of the clustering is not that fine. And also, because of the clustering, you are losing some information from agents outside of the cluster. So this is one trade-off of the clustered method. And another popular method is actually a mixture of global and local models. However, the thing is, it's still biased because you are using the global model. If without bias correction, it's still biased towards the center model. And additionally, I'm not sure if these methods can show that there is a variance reduction for the local update. So because they're combining these two updates, the total complexity, I'm not sure if there's any benefit in complexity reduction. And another popular method is called federated plus independent learning. For example, you can use federated learning as a warm start and use local fine-tuning, local independent learning as fine-tuning. However, we know that, for example, for strong convex functions, the variance will dominate the complexity. So even if you have a great starting point, in practice, you may observe a faster convergence, but in theory, the asymptotic complexity is still the same if you append independent learning to the federated warm stop. So our result, or our goals are to show the best of both worlds. So we want to give you fully personalized solutions with adaptive complexity reduction. So specifically, if your task is already close to the average task, then you will enjoy a larger variance reduction. However, if your task is actually far away from the average task, you may not have a huge benefit from collaboration, but we still guarantee that you do not perform worse than independent learning. So this is illustration of the 3 goals I just talked about. Yep.
Just to clarify, when you say complexity, are you thinking of just sample complexity?
Yeah. So it's completely regarding to this, how many data samples you need to gather to recover the solution in terms of mean square error.
I see. So in that figure, when you say federated averaging, you're just thinking of consensus, any consensus optimization.
Yeah.
The algorithm with the best sample complexity, which gives you a single model, not necessarily federated averaging. Or
Yeah.
You're just looking at the sample complexity of federated.
Yeah. I think no matter what kind of methods you use, the optimal bound is 1/n in that regard, right? So, yeah, it can be consensus or anything.
So you're going to assume something about your noise also, I'm assuming.
Yeah, we assume the variance of the data is actually kept by 1.
Sure.
Yeah. Yep. So this is our result. It's pretty simple. And again, it mirrors the title of the work. So first, we consider personalized solutions. So all the error metrics are with regard to your personalized solutions. So this is the mean square error. And we have a collaborative effect showing up here. So this is 1/n. And we have learning. So T is the number of samples collected by each agent. So you can see that 1/nt is a classic linear speedup effect in federated learning. So we have here. However, it's capped by another term. We call it like affinity-based variance reduction. So delta I here represents the heterogeneity level among agents. So you can see that if agents are very homogeneous, then delta will become closer to 0. Then this whole complexity will recover the 1 over nt, which is the maximally possible variance reduction you can get from collaborating with n agents. And if delta goes to 1, means that the agents are very heterogeneous, then this term will be 1, and this will reduce to 1 over t, which is the minimax complexity of independent learning. Yes?
So, like all the agents sample equal number of times according to this?
Yeah, so that's a good question. So we consider very stylized setting. There's synchronous sampling, independent, and we consider immediate communication. So there's no local steps. Yeah, but everything can be generalized, but we want to focus on this setup first. Yeah, because agents collect independent samples, so the maximally possible variance reduction is 1 over n. Yeah. Okay. So actually, this is a simulation of this mean square error. We can see that the ISO performance contours is actually matching the contours of 1 over n plus delta I, which is actually what is showing up in the proof, but asymptotically is equivalent to the max of these two. So there's a trade-off between heterogeneity and the number of agents. And yep. So the question is, what is delta I? I think this is the most important parameter in the result. So we first give a semantic upper bound of delta I. So this is not a definition of delta I because delta I is agent specific, but we have a universal upper bound for delta I. So it's capturing two parts of the heterogeneity. One is the environmental heterogeneity and one is objective heterogeneity. The environmental heterogeneity is defined as the maximum of pairwise total variation divergence between distributions. So you can see that this is naturally capped by 0 to 1. And the objective heterogeneity we define as the supreme norm of the difference between objective functions and divided by the supreme norm bound of the objective function. So here we have an implicit assumption is that every agent has a similar scale of the objective function, which is GB. Because you can imagine that if some agents have very small objective function that has a very small variance, they do not want to participate in the collaboration with other agents that has a large variance. So we kind of assume that the independent variance of all agents are similar, which in terms of the bound of the objective function. Okay, so because of this normalization, this term is also between 0 and 1. Okay, so this is the heterogeneity definition in our work. I think there are many other options to define the heterogeneity and similarity, but this works with the mean square error and the linear system. Okay. And affinity is actually the inverse of heterogeneity. So basically, if you have a small heterogeneity, that means you have a large affinity. That's the terminology here. And another thing, now let's go to the exact definition of delta I here. I think what's exciting about this setup is that everything is personalized. So I just gave an upper bound of the heterogeneity level, but this upper bound is system level. It captures the system level heterogeneity. But what's important here in our setup is that we want to characterize the heterogeneity level with regard to each agent. So it's defined like this. So again, it has two parts. So this is the exact definition of delta I. It has two parts. The first part accounts for the environment heterogeneity. The second part accounts for the objective heterogeneity. And it's no longer a pairwise maximum. It's actually comparing your system towards a virtual central agent. The central agent is actually corresponding to, for example, the environment of the central agent is corresponding to the average of the distribution. And objective is corresponding to the average of the expected objective. Okay, so you're not comparing you're not measuring the system level affinity. You are actually comparing the specific agent to the center. Yep.
So how does the A thing map mu I to an actual?
Yeah.
So how is the heterogeneity in mu i's related to the heterogeneity in A bar i's?
Yeah. So basically, yeah, I forgot to mention that we assume that A is the same. A is the same for all agents, and BI is different for agents. So A here, for example, we give an example of reinforcement learning, but you can also think of it as like a feature map. So extract the features of all the data points, and μi is the covariant distribution. So basically, it simply means that agents have different covariant distributions, but they share the same feature map. Yeah. We can also think of heterogeneous AI, but because it's motivated by supervised learning and reinforcement learning, we do not consider that.
How does the bound translate to the bounds on A bar I? Do you assume something about the property of operator big A?
No. We kind of assume that this is bounded, but that's it. We do not have any assumption other than the positive deafness. So we do have like a lower bound on this thing. So you can think of that if you solve this, you have inverse. So what only matters is actually the condition number of this thing. And we assume it's bounded and has a lower bound on the minimum of the eigenvalue, so everything is bounded. Yeah, that's it. Yeah, so go back to this. So we are measuring the affinity between this agent to a central agent. And the central agent is defined like this. As we said, its environment is corresponding to the average of the distributions. And the objective is corresponding to the average of the expected expectations. And the question is, so even though we are using the average of the environment distribution and objective functions, because of the nonlinearity introduced by the linear system, like linear system solutions, the solution of this central system is actually not the same as the average of the local solutions. Yep.
So the way you define delta I, it seems like it's not that adaptive, right? Like if I just add an n plus one user whose BI is like way off, going to infinity, then they're like delta I is for everyone goes to 1, even though it shouldn't really change anything.
Yeah. I think that's a very good question. Actually, there are several scenarios that this does not make perfect sense. First, as you mentioned, maybe the scale of the variance of different agents are different. One agent has a large variance, so maybe other agents do not want to collaborate with them. Another thing is that you can think of like there are many clusters very far away from each other, so they do not want to collaborate because the center of these two clusters is no near to either of the cluster. So yeah, this setup does not capture all the practical cases, but it does offer upper bound. And the implicit assumption is that every agent has a similar scale of the variance. So for example, 1. Yeah, so we do not consider the case that one agent has a significantly larger variance.
But wouldn't you say like it's kind of assuming homogeneity instead of heterogeneity?
We assume that the variance magnitude is about the same, but I don't think that corresponds to homogeneity. Yeah. So the question here is that even though we're considering a central agent, the solution of the central agent is not the average of the local agents. To be more specific, we have a scenario that, for example, we have two agents, which is blue and red. This is the solution of these two linear systems. And the central linear system has a solution that is in orange, which is pretty far away from them. This is because the condition number of the AIs can be very bad. So it will like shift the central of the solution towards the very far away. So what I want to say here is that affinity here is not with respect to the solution space. What matters here is actually the affinity in the feature space. So we want to compare like the agent solution mapped by the A bar here. So in this picture, we assume there's no environment heterogeneity, so A bar is shared with all agents. So if these agents are close in this feature space, then we have a large affinity score, which means we have a low heterogeneity, no matter how far away their solution is. I think the general idea here is that if you want to do personalized collaboration learning, and you want to define affinity, you want to find the right affinity structure. And here the right affinity structure is not with regard to the solution space, but with regard to the system space, or like a feature space. Yes.
I mean, the BI kind of captures the solution heterogeneity also, right?
Yeah.
It's some combination of A bar and X.
Yeah.
It's already capturing it.
Yeah, but if the AI, you can think of if the AI is ill-conditioned, like AI inverse will like shift a lot.
Yeah, it does capture.
Yeah, if we assume.
Heterogeneity also.
Yeah, that's true. But in our analysis, if we directly cope with the solution space, you will have like encounter some dependency on the condition number, which is not very good. But as you said, it's also, if the condition number is well behaved, it's the same. Yep. Okay, so what's exciting about this new perspective is actually we have some new results in the high heterogeneity regime. So there are two graphs. On the left is the low heterogeneity regime. The green circle represents the variance of independent learning, which can be very large. But if every agents are close to each other, they collaboratively have a very low variance. So they, in terms of delta, this is like they have small delta, and they have like a variance reduction. However, in the high heterogeneity regime, you can imagine that there's no agents alike. Then the variance of for a generic agent, it will be very large because delta will be large, right? Because it's very far away from other agents. However, if you are close to the center, then your delta will be small. You'll still get a huge benefit of collaboration, which means you have a huge variance reduction. Recall that we do not have any agent, of course B1 is here, but no other agents at the center because the center agent is completely virtual. That means even all agents are very different. Some agents closer to a virtual center will get a maximally possible collaboration benefit. This effect is also validated in simulation. So consider a high heterogeneity regime. For a generic agent, the performance of personalized collaborative learning will be the same as independent learning. However, some agents close to the center will have a variance reduction. So I think this is pretty interesting because like people usually argue that agents should only collaborate with similar agents. But now we are saying that some agents can collaborate with arbitrarily heterogeneous agents, but still get some benefit. We call it like the free ride in high heterogeneity regime. Yep. I hope this makes sense. Like in the task of color matching, you have like a blue, you have like a yellow, and if you're like green color, then you want to collaborate with those two colors similarly far from you. Yep. So yeah, this is the result we have. And now I want to try to give some like intuitions of the mechanism. So in the paper, we kind of adopt a very tutorial style. We kind of build a roadmap for all the parts. So we start from reviewing heterogeneous federated learning, and then we introduce some objective heterogeneity and the personalized collaborative learning setup. And to deal with this objective heterogeneity, we introduce a specialized bias correction mechanism. And this term, we need to know the central objective, which is the BC here. The central agent, the central objective function. We need to know that. If we don't know that objective function, we can introduce a central objective estimation module, which interestingly can be cast into a multi-agent linear system. So we can solve this problem in a similar style as we solved the original problem. So that cope with the unknown central objective. Then we can introduce some environment heterogeneity. And to cope with this, we introduce an importance correction mechanism. And again, to do importance correction or density ratio correction, you need to know the density ratios. So we have a density ratio estimation task module, which again can be cast into a multi-agent linear system, can be solved using our method. So this is the whole pipeline of the algorithm development. So let's briefly,
So,
yep.
I don't see how you get the funnel rate. Your funnel rate, if delta is small, is of the form 1 over n times t.
Yep.
Right. But if delta is small, how do you know this? Are you estimating this?
Yeah.
But
We're
are
not
you
estimating.
it?
No, we're not directly estimating delta,
Okay.
but it's adaptive to that.
Yeah. What is the adaptation procedure?
We'll show the mechanism. Maybe it will be clearer there.
Okay.
Yeah.
So, can I ask one more question?
Uh-huh.
So, under your assumption delta I for each client, what's the guarantee you get for the consensus protocol, what you call federated averaging in that?
Yeah.
What's the guarantee you get there?
1 over nt. You mean?
But how does that guarantee depend on delta I under your assumptions?
No, it does not depend on delta. So when we review the heterogeneous federated learning, so there's heterogeneity, but we still can get a 1 over nt complexity.
No. I'm talking about not your algorithm, but the algorithm that you called federated
Yeah.
averaging in that figure.
Yeah.
If that gets 1 over nt, then isn't that already better than your algorithm?
No, you only produce a unified solution, but not personalized solution.
But how does that matter if I give that solution to everyone?
I think he means 1 over nt for your target, for your personalized.
Yeah.
Measured on your. on
Yeah,
your
but the
personalized
delta I can control how bad is the consensus solution on each of the clients. Because delta I is already indirectly controlling how different the clients are.
No. So he just has a baseline. There is the average, and then
Yeah.
the personalized is am I delta I far from the average? If I am, then if delta I is large, then I use the personalized. If not, I use the average.
Yeah, sort of.
Right. So all I'm asking is the B.
Uh-huh.
What's the guarantee for
Yeah.
B under your setup?
Yeah, so it will return a solution that is very far away from personalized solutions, but it will have a very small complexity due to the variance.
Yeah, but how far it is from the personalized
It
solution
depends on
will
delta.
depend on delta.
Yeah.
So that's what I'm. So the minimum of A and B,
Yeah.
is it better than your algorithm or no?
So we will be fully adaptive. So we will. That's a good question. So basically, you can control a threshold depending on
I just run
delta.
A, I just run B.
Yeah.
With half samples and then return the best for each client. Either it's coming from A or it's coming from B.
Yeah. I think you only.
So the issue there is that you cannot get the minimum of those two, right?
No, for each client I'll get the minimum of A and B. I don't know if I'll get the minimum of 1 over n and delta I. I'm asking whether in your setup what do you get if I just run the algorithm minimum of A and B.
What do you mean by?
So for each client I run both A and B. For each client I either return the model that comes for that client from A or from B, depending on which one's better. This is my algorithm.
What is the better? Like they have different metrics, right?
On their metric.
Okay,
On
so
the
it's independent learning.
Yeah. So not independent. So on each client's loss, I either look at their independent learning model with half the samples, or I look at the what you call the federated averaging model on half the samples.
Yeah.
If whichever is better on that client, I just return that model on that client, and I do this for all the clients. In principle, each client could get a different model. All I'm asking is under your assumptions and for this problem, can you beat this algorithm?
So I think definitely you can beat independent learning because you are leveraging some similarity.
Yeah, but okay.
Yeah.
Can you beat both of them at the same time is the question.
For federated learning, as we argue that for generic agent, and if you're very different from each other, it will not. But for some specific agent, for example, you are at the center of like 3 agents, you'll get a 1/3 speed up.
So do you agree that my protocol is a personalized learning algorithm?
I think is.
Can I?
Yeah.
I think for the sake of time, we probably should continue.
Okay.
But I actually think that what he's proposing here is strictly better than what you just proposed.
Okay.
For a simple reason, if you're testing on your individualized thing,
right,
you are bound to the number of samples you have there. You split, right? You are bound to the number of samples you have there. He's able to get 1/nt.
I think
I'm close.
We need to discuss it offline. I think I understand that, but okay.
Yeah, I think there's some similar, equivalence there, but we can discuss later. So let's introduce the algorithm. It's pretty simple. So first we have independent learning and federated learning. So for federated learning, you update your parameter using local update direction. for example, gradient descent direction, or in our case, is the residual of the linear system. And for federated learning, you just aggregate all the update direction. And so we propose a personalized collaborative update direction, which is a combination of these two, which we use local update direction. And we also want to use the central update direction, which has lower variance, but it will introduce some bias towards the center. So we introduce a bias correction. And also because of the environment heterogeneity, we also need to correct the density ratio difference. More specific, the goal here is that we want this update direction to be unbiased and also have some variance reduction. I think it is related to your question. You can get a smaller mean square error without using an unbiased update direction. But here the mindset is that we want it to be unbiased no matter how delta is, how large delta is. But so we want these two goals. And more specifically in this linear system setup is that the local update direction is simply the residual of your current parameter evaluated at your current data point. And federated learning is simply aggregating all the local residuals. And we denote it as GI and G naught. And so for some personalized federated learning, people argue that we can use a combination of this local and the central update direction. But I argue that this will always introduce some bias towards the center. So we want to propose a bias correction term that completely removes the bias in the central update direction. And the question is like, how do we choose this bias correction term? So it will be, so first let's assume there's no environment heterogeneity. So A is the same for all agents. There's no distribution difference of the data. So what we need to choose is, in the bias correction term, what is the objective? So intuitively, it should represent the central objective, right? Because we want to correct the bias in the central update direction. So this bias correction term should use the central objective. The thing is that there are so many candidates that you can use in this bias correction. They will all give you an unbiased update direction. But it's very hard, not very hard. Like it's a little bit difficult to reduce the variance of it. So for example, commonly used in federated learning, for example, scaffold by Professor Karim Reddy, and also personalized collaborative learning by Professor Stich's work. There are some like bias correction terms, but it may not give us a variance reduction because you can think of it like your local drift is essentially personalized. So that is not gonna be like improved due to collaboration. But once in the federated regime, your local bias correction will be aggregated at the center. So that will introduce a 1/n variance reduction, federated variance reduction. But here we are doing the other way around. We're not correcting the local drift towards the center. We're actually correcting the bias in the central update direction towards the local solution. So that part will never do an aggregation. So that part is personalized. The bias correction term is personalized, but never aggregated. So that part, you will not have a federated variance reduction. So what can we do then? We will not have a 1/n speedup, but what can we do is to introduce some correlation between bias correction term and your local update direction, right? Due to this correlation, so what we propose is that you evaluate the central objective function on your data point. Because of this correlation, then this whole thing can be think of as a control variate. Then you will introduce some variance reduction. So this goes back to your question about how do we achieve variance reduction. It's not in terms of n, but it's in terms of how close your objective function is towards other objective function or the average objective function. And if this is close, then this control variate will give you a larger correlation. Then the term bias, the variance of the term will be smaller. I hope it makes sense. Yeah, so basically in the bias correction term, we're not only looking for correcting the bias, we are also looking for reduced variance. To achieve this, we correlate the bias correction term using our local data, and that will give us a affinity-based variance reduction. I hope this makes sense. Yeah, then, so first we assume there's no environment heterogeneity. Now we assume there's environment heterogeneity. Then you can think of like, because we introduced the correlation by using your local data for the bias correction term. So this data comes from your distribution, but the central update direction actually are using data from a central distribution, where there's a mismatch between the two. So what we propose is simple density ratio correction. Again, if we are only looking for unbiased update direction, we can actually add the density ratio correction to either term, right? Because the expectation will cancel out then. The question is, how do we achieve variance reduction once we introduce the importance correction? And so we argue that you can only do the importance correction at a center. So yeah, this is the proposal. To see why, we have 3 observations, but let's first expand the definition of this importance corrected central update direction. So basically, it's an aggregation of importance corrected like information from others. So we have 3 observations. The first observation is that the density ratio here has a natural upper bound by n. So this is not the case in other areas using importance sampling, which is frequently, like people frequently encounter like large variance due to importance sampling. For example, in covariance shift or offline reinforcement learning. But this is not the case here because we are in a collaborative setup. So you always contribute 1/n portion to the central distribution. So this has a natural upper bound by n. N is not good, but it's an upper bound. It's not going to infinity. Another observation is that the chi-square divergence between these 2 distributions are like upper bounded by the density ratio supreme norm and the total variation divergence. And this is naturally bounded by our heterogeneity definition. And the third observation is that the variance of this importance corrected central update direction is bounded by this term. And we can see there's 1/n here. So this is pretty important because we're considering the central update direction. So whatever happens in the center, we can always hope for a 1/n speedup. So you can see that combining these 3 observations, the upper bound n and the 1/n here cancel out. And what we left is actually this term. And this term is actually exactly the definition of our environment heterogeneity. So this is what we hope for. There's a 1/n here, and there's a delta environment here. But what if we apply the importance correction to the to the bias correction term? What will happen is that first we lose the natural upper bound. This term can be unbounded. And the second thing is that we do not have a 1/n speed up on the client side, right? So together, if you apply the bias correction, importance correction to the bias correction term, the variance can go to infinity, especially when the heterogeneity is large. So this is why we argue that you should apply the importance correction to the central update direction. Okay, this is just some mechanisms. Any question? Yeah.
So you know the mu's?
Oh, yeah, the good question. So here we kind of assume we know the mu, and if you do not know mu, you can apply a density ratio estimation. There's like a wide range of literature on this, but there's a caveat. There's some lower bound here, but I'm not gonna expand on this. So if you know nothing about the densities, maybe you cannot achieve the whole thing, but yeah, there's a lower bound there.
So like if you try to sample and estimate the mu's, do like some noisy estimate to get good algorithm working?
Practically yes, but yeah.
Would you incur too many samples just to estimate the ratio?
That's true. Yeah, the lower bound applies to density ratio estimation. So we do not do that. So we have to assume additional structure on the density ratio structures. Yeah, there's many famous lower bound in density ratio estimation. So yeah. So any other questions about the mechanism here? Okay, so this is just one of the preliminary work. I think there are many exciting directions. first we want to generalize this to nonlinear system and the optimization problems, which poses many challenges. I think the biggest challenge is how do you define similarity and the heterogeneity in that kind of regimes. Here we define it as like a total variation distance and the L2 norm distance. But for these systems, you may need to define other structure of the similarity or affinity. Another question is, what is the lower bound of the sample complexity? So we show that our results actually interpolates between two ends. One end is federated learning, one end is independent learning. For those two ends, these are minimax optimal rates, but in between, we do not know if our result is optimal. And also, what is the information? Because, for example, in order to estimate the density ratio, or in order to estimate the central objective function, you have to send some more information. But if we do not have that like channel or like complexity resources, what is the minimum information exchange needed to achieve any benefit from collaboration? I think that's also an exciting direction. And again, other affinity structures can be considered. Here we consider like the low magnitude complexity, but also there are other affinity structures such as sparsity or like low rankness. These are some exciting directions. And the final takeaway is that we show that collaboration between arbitrarily heterogeneous agents can yield fully personalized solutions with an adaptive affinity-based speedup. Yeah, thank you.
Any questions?
Ask, but I have already asked.
So I have one question.
Yeah.
So like, how do you think like sparsity could help?
Yeah, for example, sparsity definitely helps in the density ratio estimation because in general, L2 norm cannot be, if you consider L2 norm, then the error cannot be reduced in the density ratio estimation, but you consider L1 norm or L0 norm, then there's a chance if they are close in that norm, that will have like lower complexity in estimate the density ratio. And I think it applies to objective function and as well. Yeah, so I imagine a similar bound applies. Mm-hmm.
Okay, thank you very much. Let's thank the speaker. Like, any more questions? Okay, yeah, if there are no questions, let's thank the speaker.
I don't know if your microphone is working.
Oh, yeah. Is it working?
You can hear me.
You can. Okay, I guess. Yeah. I will just.